All right, so let's look at the homework. Let's see, 9 resistors. Let's see. Some of you get scared because there's more numbers, but I made it easy. I gave you all the resistances. Okay, and all you have to do is you can do the first part, you can do the next part, same thing again, and the next part, same thing again. All right. Let's draw it out. Okay, 9. And 1, 2, 3. What did I do? Oh, sneaking back and forth. 3, 4, 5, 6, 7, 8, 9. We said the voltage is 20. So we can say voltage, current, resistance, power, total. Oops, I missed one. All right, so let's see some values. Let's start at this end. We'll say on the resistance column at 15 ohms, 27 ohms, 39 ohms, 56 ohms, 22, 12. That's pretty small value. Oops, I got off one. 22, 56. Oh, my last one right here. Okay. So 6 was 47, and 5 was 56, 22, 12, 33, 100, and we said that's 120 volts. Okay, so do we have any 2 items in any of the columns based on that given information? Yes, no, maybe?
Any 2 items?
Yeah, in any one column, do you have 2 values?
No.
So therefore, we can't just do the math anywhere there, right? We're gonna have to do some analysis, right? We do have all of the resistance values except for R sub T. So using series parallel Kirchhoff's laws, we can do the analysis to figure out what R sub T is, right? In fact, at this point, I think that's the only thing we can solve for. We can also say that given all the current has to go through 1 and 9, probably the most significant voltage drop is going to be across number 1, given that's also the highest resistance resistor. Okay, so of the 120 volts, I'm going to say probably 80 or so of it is dropped across number 1, some fairly high value, just rough guessing. So, with respect to doing the series parallel analysis, the first rule, any place we can combine parallels or combine series without doing series parallel. Does that exist here?
Mm-hmm.
Can we do any parallels? Doesn't look like there's any parallel, just parallel branches that are pure parallel on their own. Right? But it does seem like there are 3 series loads in series all on their own without any parallel in between them, right? Seems like 3, 6, and 7 could be combined into one value. You okay with that? So 3 is 12, 6 is 47, so that's 57, 59, and 7, 59 and 39 is going to be 89, 98. Right? So I can say this value right here, combined as 1, is 98 ohms. Right? Is that a legitimate statement? Presuming my math was correct? Okay, now, do we have any pure series components or any pure parallel components?
1 and 9 are series.
Well, but I can't really add them together at this point because there's a bunch of stuff in between them, right? So I can't really do much with them until I know what the current is going through them. However, at this point, I have a value that's the sum of 3, 6, 7 called 98 ohms, and that is purely in a parallel relationship with number 5, which is 56, right? So I can do that combining. So I've got to use my 1 over formula, 1 over 56 plus 1 over 98. Okay, I know it's going to be less than 56. Given that the ratio of those is 2 to 1, I'm going to say it's about a third of 56, which would be what, 35, somewhere in there? 35.6, is that what that all that works out to? So we can say all of this equals 35.6. Give me a couple more. 63. Well, we can say 6. That way we're not truncating. Oh, I forgot my little homies. Okay, so we can say that equals 35.636. If I combine all 5, 3, 6, and 7 into one resistance value, that equals 35.636. Now, do I have some purely series component using that value? Can I take 2 and 8 and add it to the 35.636?
Yes.
So 2 is 33 and 8 is 27. That looks like 60. 90, add that to the other one, it ends up being 95.636. So when I take and add that in, I end up with 95.636. I can now do parallel this to 4. Okay, 1 over 95.636 36 plus 1/22, I know the value is going to be less than 22, but the 95 isn't going to have a whole lot of impact on it. So I'm going to say it's going to knock it down by something less than a quarter, maybe 18 something. Rough guessing. Somebody want to plug that into the calculator?
$17.885.
17.885. Well, my guess of 18 was pretty close. So all of this is 17.885 ohms. All right, so now the only thing that's left is a series component, right? So if I take 1 as 100 and 9 as 15, that's 115, and 17 would be 132.885, and that's going to be R sub T, right? Okay, 132.885 ohms, and that solves for R sub T. Everybody okay with that? All right. Now what do I need to do? Don't I have to divide that into 120? Well, it's pretty close to 120, so whatever my value is going to be slightly less than an amp. 0.9 something. That would be, yeah, about 10% left, because 120 and 12 get you to 132. So, so what do you say? 0.9030?
Yeah.
Well, we'll put the 0 there just for giggles. Can I plug that in anywhere else?
189.
Isn't all the current going through 1 and all the current's going through 9? Okay. 0.9030. And all the way over here, 0.9030 amps, and amps. Okay. So now I've got, again, a couple in column 1 and a couple in column 9, so I can do some solving there. 100 times 0.9030 is pretty easy math, isn't it?
90.3.
Okay, you just move the decimal place. 903 volts. Remember I said it was going to be 80 somewhere in there? Right? Okay. 15 times 9030. Well, that would be 1 decimal place over plus, say, a 0.4 somewhere in there. So 1.4 or 1.
13.545.
Slightly less than 15, that works. So 13.545 volts. Now here's where some of you guys get a little bit lost. What we're going to do is we're going to start at 0 here and 120 there. We're going to get these node voltages. Okay, so 0 plus 13.545 volts there. And here, 120 minus 90.3 should give me 29.7, right? Is that correct? Did I do that math too fast? In my head, I got it wrong?
You're adding up.
I took the 120 and I subtracted the 90.3 going down, and I took the 0 and added the 13.5 or 0.545, because I'm going to go up on the negative side and down on the positive side. Okay, I know what the voltage drop here is. or in this case, it's the voltage rise. Okay, so that's going to be 13.545, and that's going to be 29.7. The voltage drop across 4 is going to be the difference between these two, right? You guys are looking at me like, okay, this isn't any different than all the other ones I gave you. So the voltage dropped 13.545 from 29, I don't know, 16, 16.1 something,
155.
155. So 16.155, and that's going to be felt across number 4. 16.155 volts being felt across number 4. It's also going to be getting felt across 2, 3, 5, 6, 8, 7, 8 as an array. Okay. However, the only thing I can really calculate right now is the current that's going through 4 and isn't going through 2, 3, 5, 6, 7, 8. So at this point, 22 divided into 16 must give us a number that's smaller than this, because this is current total. Right? You can't make current here. I had one of the students this morning get negative current. Like, okay, well, we could pretend that it's a DC or an AC circuit. Okay, so 16.155 divided by 22.
0.7343.
That seems about right. 0.7343 amps. So some percentage of this amperage is going by number 4. The rest of it's going through 2 and 8. So if I subtract this from here, that's what must be going through 2 and 8. Right? So it's not going to be 2, it's going to be 0.16 something.
1687.
0.1687. And I'm going to plug that in number 2 and number 8. So what do we say?
687.
687 amps and 0.1687 amps are going that direction. Okay, now I can calculate the voltage drops for number 2 and number 8. 33. Don't we do a multiplication there? 33 current times resistance equals voltage. So 33 times 1687. Let's see, 3 times 16 would be 48, right? Plus a little bit. So probably going to be 5 volts somewhere in there.
Yeah.
5.567.
5.567. Really? Volts, okay. The voltage drop here is going to be a little bit less. So my guess is it's probably 4.8.
4.554.
Okay. 4.54.
554.
554 volts. So now I've got to do my node voltage again. So I'm going to drop 5.567 here, and I'm going to add, I can't see it,
554.
4.554 volts here to get to the new node voltage. So if I've been keeping a running tally, well, it looks like I have been keeping a running tally. Okay, so 13.545 and 4.554 4 at 17, 18. Oof.
Subtract.
Actually, it's pretty darn close to just slightly under 18. Oh no, it's 18.1 or 18.09. Am I right or wrong?
18.099.
Okay, so the node voltage here is 18.09, you said?
099.
099. Okay. Volts. We're going to take 29.7 and subtract 5.567. So that's going to give us 24.7 minus 556 is going to be 24.14 something.
24.133.
24.133. Okay, 24.133 volts. Okay, that's the node voltage here and here. The voltage drop across number 5 is going to be the difference. 18.099 from 24.133, which is going to give me 6 point something.
11. Your mind.
I'm going to take the 24.133,
Oh, 24.
my node voltage, 24.133, and I'm going to subtract 18.099. Should give me 6.1 something. 6.033 being felt across 5. 6.033 volts being felt across 5. Voltage drop. Now the only thing left that I can calculate at this point is the current going through the branch of 5, and it's really the remainder of what came through 2 and 8. Okay? So 56 into 6 is going to be a really small number. I'm not even going to try and do that in my head.
The amperage, it's for R5,
Yeah.
it's 0.1073.
0.1073.
Correct.
Okay. Well, that's definitely less than total amperage. It's also got to be less than what's going through 8 and 2, which it is. So now this value tells us what's going through 5, but the remainder of what's going through 8 and 2 must be going this direction, right? So that means I can take either 2 or 8 and subtract this 1073 from it. That ought to get, let's see, that'll leave us with a 6, a 1, and a 4.
0.0614.
0.0614, and isn't that going through all of 3, 6, and 7?
Correct. Mundo.
So 0.06, I forgot what it was.
0614 is what I got.
0.0614 and 0.0614 amps.
And we're done.
So at this point, we can now, we don't even need that anymore. We can just do our math up. Then what we're going to want to do is do our math all the way down to here, do the math here, add all those up to make sure they equal that, and you know you've got it pretty close to the ballpark. Right? Okay? That wasn't any different than some of the other ones we've done. It's just one more layer of parallelism there. Okay. Well, the resistors don't get the work out.
If we have time, can we go over transistors, turning them on and off, you know, with the, when you basically have a pull down resistor, a variable pull down?
Well, pull down or pull up, depending on which way you're going.
Yeah, go over that whole circuit, and, I mean, I understand how the junction gets turned on, but I don't really understand like the loads, in respect to that junction, how that works.
I'm not understanding, so.
Yeah, well, I wish I could formulate a better question, but I don't know if anyone else is understanding it or not, or.
Okay, so let me see if I can find it.
It would be like on,
Go back to the digital one.
my slides aren't numbered here, but you have an example of transistors with NPN and PNP, and then you have,
Yeah, let me just go back to digital components.
oh, sorry, that's, I didn't realize it was that far back.
Well, I'm just reasonably certain there's gonna be one there.
Yeah, right there. That's one example, sure.
So ultimately, this guy is going to want to let electrons go one direction and or one direction either way. This one is the same thing, it's going to want to let electrons go one direction and either way. Okay, if I let electrons go towards the middle value, then it will open the path this way. If I let electrons go towards the middle value, it will open a path here. So if I let the electrons see negative, a lot of negative, so if I let a bunch of electrons come in here and go that way, it'll turn this on. So the way to do that is make this resistance lower than that resistance.
Okay.
If I make it quite a bit higher, then this will see this circuit here as a P more than anything else.
And the load's always on the collector side.
The load is usually on the collector side, and it's a collector of holes. Okay, but collector and emitter flip whether it's NPN or PNP. So it ends up being, so this is the collector and that's the collector.
So why do you have an extra resistor above the variable resistor then on the, it's like it's.
No, I have a voltage divider on both.
Right. Okay, so that's.
So they're both just voltage dividers. The only thing I did different is I put the variable resistor on the side that I'm going to want to control on. Okay, I could control it from the other side. You know, I could put the variable resistor on the opposite side. We just typically put it on the side we're going to control from.
Okay.
So here I need to control in. Okay, so I'm going to control it here, and this is just the pull off resistor. This is just there to shut off the transistor. Same thing here. Sending this to P is going to turn it on and off. I could get rid of this altogether.
Mm-hmm.
The problem is, unless this resistance would way up, I'd still get a little bit of leakage.
Okay.
Okay, same thing here. Without that portion, unless this resistance went really, really high, I'd still get a little bit of leakage. So this, once the ratio from here gets somewhat significant, this guy is going to be enough to where it'll completely shut this off.
Okay. Yeah, I get it. Thanks.
Okay. Yeah, the whole purpose of the other side of the voltage divider is just to ensure it truly does shut off. We often use transistors because it uses so much less current as a switching device versus an analog device. If the load was a speaker, an audio speaker, it's purely analog, okay?
Mm-hmm.
And that transistor is going to get really, really hot because it's going to be acting like a big variable resistor. So it's going to need a really big heat sink. On the other hand, if it's like a field regulator that's either switching on or switching off, when it's switched off, there's no current, so that guy doesn't get hot. When it's switched on, all the current's going through there, but there's very little resistance, so it doesn't get hot. Okay? It does get hot from the current going through it, but it's not dropping any voltage, any significant voltage. So it doesn't get nearly as hot. When it's somewhere in between, that's when it's got a lot of current going through it, and it's a fair amount of voltage drop, so it gets a whole lot hotter. Okay, and we will in fact design the transistor very differently for switching versus analog use. Okay, so I think we were in the middle of avionics. We were just talked about modulation.
Yeah, we were monopole versus dipole.
I thought I'd thrown out the idea of amplitude and frequency modulation.
And my notes say antenna types. Maybe I was asleep. I don't know.
Yeah, but so I thought I talked about this, so we'll cover that. That's where somewhere in here. So let's start there. I know I had mentioned frequency modulation and amplitude modulation. So in this particular one, this is me singing badly, right? I never sing goodly. So me singing badly, I'm going to have to take and make a carrier wave of some kind to get it to transmit. Okay, so somehow or another, I'm going to have to be splashing the pond to get data transmitting. Then I'm going to vary how I splash the pond. Same thing is true with smoke signals. At some point, I got to start a fire and make smoke, right? Then I got to start making breaks in the smoke, because a straight stream of smoke, all that tells you is call the fire department, right? Okay, if I want to start making data, I got to start putting pulses in there, then vary the pulses to get some value, some useful value. So here we're going to have pulses, and we're going to vary it based upon whatever data I want. So in this case, I'm going to vary the amplitude at a very constant frequency. And that's AM, or an amplitude modulation. In this particular system, that allows me to have a fairly narrow band of, in other words, my channels, you know, channel KGB and channel KCBQ and channel, you know, whoever, can be fairly close to each other. However, we first went with amplitude modulation because we couldn't get our channels very close to each other. They had to be, the each carrier had to be pretty far apart because our tuners just weren't that great. Once we got better at doing this, well, too late. We'd already defined all the bands. And so we couldn't come back and say, well, okay, all you guys in the world of radio broadcast station, you got to spend billions of dollars buying new equipment. And all you guys with airplanes and all that federal navigation equipment, you all got to buy a bunch of whole new equipment. Couldn't do that because it was cost prohibitive. So aviation stayed in amplitude modulation for all their comm and nav work. Others, as we got better and better at this, started going over to other systems. So, for example, the other most common one, which I think does a better job of transmitting data so you get the digital, was frequency modulation. So in frequency modulation, the drawing is very extreme. What we really said is, if your frequency is going to be somewhere behind, of course I put it right in the middle, didn't I? Okay, if my frequency, let's say, you know, what is it, 101 KGB, 101.0 KGB, I don't know what it is, KPRI, whatever, I'm making it up as I go. Whatever that value is, what we really want to say is there's a range. So maybe we'll say from 105, 100.7 up to 101.3. That's our frequency range. When I'm down at 101.7, I got very, very low tones. And when I'm very up high at 101.3, I'm very high. I can't do it, sorry. Okay? So, very, very high tones, and then very, very low tones. I'm going to get slower, or higher, or slower. So now my channel actually has a little bit of width to it. So that means I can't fit as many channels over some bandwidth, right? So I'm gonna have to make sure my tuners are pretty accurate. Well, this is why, particularly as you're driving down the road and the signal starts getting a little bit weaker, and you got another one that's pretty close to it, and they're both reflecting and echoing, and Doppler effect is occurring. Sometimes on FM particularly, you'll hear two channels bleeding over, okay? Because they're close enough to each other that the next channel, whatever it is, 103 and 101, they're close enough to each other that you start hearing both of them, okay? So what that meant is, for the FCC, the agency that does all this, they had to say, well, okay, for Southern California, this is how powerful you can transmit. And we're gonna put this frequency there, that frequency there, that frequency there, that frequency there, that frequency there. And they're all separated enough to where they won't bleed over to each other too much. Okay? However many different frequencies in one region. And then they made all this big matrix of all the different frequencies so that they'll repeat themselves once you get kind of far away, and there's no chance that the strength of the signal will get all the way to where that repeat exists. Right? Everything's golden. Except somebody came along, bottom side of the United States, and drew a big line to mark the bottom side of the United States. And everything below that big line, the United States rules don't apply. Because it's not United States, it's Mexico. Mexico says, well, hey, we want to make a little bit of money, so we're going to set up our big old antenna and start broadcasting madly with whatever frequency we want. Okay, what do those guys up in the United States want to hear? How about country music? Okay, let's give them some country music. So we'll put out this radio station. Well, you can see fairly quickly that the United States and Mexico need to start sorting it out, or they're going to start shooting at each other. Okay, over frequency, right? So part of the reason that one chart about bandwidth, all those different bands, but they also had to hammer out sort of regional agreements so that our radio stations aren't bleeding into their channels and their radio stations aren't bleeding into our channels. Does it work that well? Yeah, yes and no. When we went into the digital world, it started turning out that, yeah, we get a lot of bleed over. You get anywhere near the border, it's fairly common for your cell phone to suddenly start listening to one of the cell towers across the border. It's true up in Canada as well. And as soon as it does that, they start, in fact, any time it could possibly do it, they do it so they can start hitting you with international fees, right? Okay? My general sense is, and it would take a class action suit, but my general sense is enough folks got together, they could go after the big cell providers. All right. So, shaping antennas. So it turns out when we set a monopole antenna, we're going to stick this big antenna up. Or I can be a dipole, I'm going to stick it way up. And I'm going to radiate out in all directions, right? Only there I am on top of Mount San Ysidro, or San Miguel. There's a bunch of radio antennas on both of them. And Mount San Miguel, it's right behind Sweetwater Reservoir. Okay? There's absolutely nothing to the southeast of there. Well, except for Del Zura, and who cares about Del Zura, right? There's absolutely nothing in one whole quadrant, maybe even a third of a quadrant. So there's no reason for them to transmit a whole bunch of energy that direction. So if they can shape the antenna so that it fans out this way, a bunch of the antenna fans out this way, it's to their benefit. Okay? I may also need my waves to go this way or this way, depending on what I'm trying to do. Particularly if I'm trying to use them for navigational purposes, right? So I might have vertical polarization or horizontal polarization, in which case I'm going to orient my antenna and shape it this way or that way. Another thing that's going to be important is what are you attaching it to? If you're attaching it to planet Earth, well, just drive some spikes into the ground and hope the wind doesn't blow too much. If I'm mounting it to the airplane, you know the wind's going to blow quite a bit. Otherwise, it's not really an airplane. Okay, it's a piece of art. Right? So at that point, I'm going to have to take into account for the structure and the wind loading on that antenna. Certainly in ground-based antennas where you're trying to get altitude, wind loading can be pretty significant. Okay? I remember one time I was flying down Highway 90. It was all across the United States, about Minnesota level. I was flying along, talking to some good old boys, and this guy from FedEx at 30,000 feet jumps in and says, "Hey, where you at?" "Oh, I'm down here flying along." And he said, "Oh yeah, you know what? Are you above 4,000 feet?" It's like, "No, I'm down around a couple hundred feet because it's more fun down here." He said, "Well, get on the north side of Highway 90 because there's an antenna on the south side. You're probably not too far from it." "Oh, okay." We'll go over pretty soon. 4,000 foot antenna goes whizzing by. Okay, 4,000 feet up. You know how far out the guy wires, right? The guy wires, they're several miles wide, and you can't see those. Big fat wires, but you can't see them in an airplane. It slides the wing right off, right? I was pretty grateful for that guy. It was one of those days where it was like 3 miles visibility, maybe. He clearly had flown the route enough times to know. But they got some pretty tall antennas. Can you imagine the wind loading on all those wires and the mast and all of that when you get a nice, South Dakota blow going? Anyways, it's has stood the test of time, at least to this point. So the other thing is, if I put the antenna next to a big tall building, or the vertical stabilizer, or pretty much anything else, the way it emanates electromagnetic radiation, it's going to cause echoing and all kinds of weird things. And it's just like if I took my pond and had a big wall over here in the middle of it and started dropping my rock in there, okay, it's going to radiate out until it hits that wall, and then there's going to be reflections coming back, and they're going to interfere with my original reflections around where they're bouncing into each other. The ones going this way, you'll never have a problem. But I'm going to have to be pretty careful about other structures. Well, one of the things you kind of have to bear in mind is one of the structures that doesn't look like a structure while the airplane's sitting on the ground is the propeller. The propeller, when it's spinning, acts like a big metal wall that's 72 inches in diameter, or 76 inches in diameter. As far as electromagnetic radiation is concerned, it's just a big round metal disc. So it's not going to penetrate through it very well. So mounting the antenna on the fuselage, it will interfere with forward projection if that's important to you. Now, a lot of times what we'll do is we'll mount it on the fuselage, but up on a vertical stabilizer, so it's up high, so that 72-inch thing is sort of shifted off a little bit, and it can get around it fairly easily. Obviously, you don't want an antenna to create turbulence or anything else that will affect aerodynamic performance of a trim tab or of a control surface, or maybe even a fixed flying surface. Probably not a bad idea to make the antenna somewhat aerodynamic in shape. It will help it. So if I make the antenna a big round thing versus a teardrop, that big round thing is going to have a whole lot more drag. Okay? Because the formula for the drag includes cross-sectional area. And what is cross-sectional area of a circle?
It's pi r
Pi
squared.
r squared. So once you put that exponential function in there, you start getting big, the amount of drag gets really, really big. Now, most antennas only need to be a quarter of an inch in diameter or smaller, so it's not going to be too bad. But we could save a little bit, particularly if it needs to be a fairly long antenna, by making a little bit of a teardrop shape, or at least the base might be teardrop shape. We're going to need to make sure that it doesn't leak water into the cabin. It doesn't promote or incite icing to form. We also don't want it to trap water. So if water gets trapped in somewhere, it can either corrode or freeze and break stuff. The last thing, if we can prevent lightning strikes, we should, but there's only so much you can do there. Lightning's pretty magical. It's going to do what it wants to do. So really, antenna location is very, very critical, and it can be a real bear. This is one of the reasons why, if you're going to put an antenna on, you can get an STC for the specific airplane. In all likelihood, they've done a pretty good job of mapping out where it should be on that airplane. The one gotcha, though, that they don't know is where other antennas are. In general, you do not want any receiving antenna anywhere closer than 3 feet. It's got to be more than 3 feet away from any other transmitting antenna. Okay, you could have two receiving antennas together, fairly close. It's not going to cause, usually not going to cause too much of a problem. But anytime you have a transmitting antenna, you're going to want all other antennas to be at least 3 feet away. Well, that can get kind of difficult, okay? Because there's not too many places you can put it, on a small airplane. If you've got, a couple of radios, a couple of nav devices, a GPS device, which may or may not be transmitting, a transponder or two. If it's got ADS-B, it'll have a second transmitter, maybe. So passive receivers, you can usually get away with being a little bit closer, although oftentimes they'll tell you it's 3 feet from anything else. You may also want them to be a little bit far away from any high current user. So if it's coming out the bottom of the fuselage and the battery box happens to be right there, might not be a good idea. So again, it's not universal, but typically you're looking for 36 inches or more from anything sticking up, including the exhaust pipe, the propeller, whatever else. So if it's a dinky little airplane like an RV-3, man, you're taking that tape measure and doing all kinds of stuff and trying to figure out a spot to put that last little antenna. And of course, by the way, wherever you put the antenna, what else you got to do?
Route the wires.
Well, you're going to have to get a wire to there, so it needs to be a place that you can actually conveniently get a wire to. You also are probably going to have to need to get in behind where the antenna goes and put a doubler of some other type and maybe do some riveting or some other structural improvements. Okay, that's going to weigh heavy on you. If the manufacturer of the antenna or the system you're putting in doesn't provide that information for you, where would you find it?
4313. 2 Bravo.
4313.
2 Bravo.
2 Bravo. Why 2 Bravo?
Because it has the antennas chapter in it.
No. That's because 2 Bravo is acceptable alterations. 1 Bravo is repairs. 2 Bravo is acceptable alterations for common things, like installing antenna, skis, floats, oxygen systems, something like that. Those are all considered alterations. 99% of the time, the FAA is going to say, yeah, major alteration. Okay? Okay. So yeah, you got to be able to get in there and hold their bucking bar and or get the cable there and you know, take your arm and you kind of tie it down and stretch it out an extra 6 inches back. Get it good and long. Then stick it in there real quick before it stretches back. Okay? Or you go find a small guy like Paul and throw him in the tail cone. Okay? Yeah, rent a small guy. Hey, we can start a program there.
It'll cost you a lot.
Yeah, they cost you a lot. Well, they're called kids, aren't they?
Nope.
Yeah, they cost you a lot. Well, does it change depending on whether or not the bucking bar hits you?
It certainly does.
Okay. It depends on the temperature too. That tail gun can be pretty hot back there. So yeah, and again, that doubler, if it's a fabric airplane, now you got some real serious issues, don't you? You're gonna have to find a place in there, and it's gonna be kind of hard to mount because you're not gonna be able to weld it in. You might have a situation though, where, you know, you've got your fabric, and you've got a tube here and a tube there. You can set up an ADL clamp and an ADL clamp like that, and then put a plate, slide a plate in there with a couple of, a couple of flush screws. You're going to have to work very carefully to get those in place. Now that you have that plate in there, you can then come through the fabric as a doubler, as your hard point. Okay, so again, depends on what you're doing. The antenna base, there's really two basic kinds of antennas that mount. There's one kind that comes down like this, with a nut, and there's sort of some insulators that sit in here, and that's an unbalanced antenna lead. So monopole antenna. So somewhere in here, you're going to need to make a ground plane. The other more common type antenna will have a base assembly that's sort of shaped like that, and it's teardropped. Might have 4 screws going down in like this. The antenna comes up and maybe it does something like this, and then it'll have a B and C connector to it. And this base actually will have some tuning components in it. This base needs to be securely grounded to the ground plane, or in this one it doesn't get grounded to the ground plane, but you have to attach to the ground plane with your other unbalanced lead. And then of course length is going to be very critical on either one of those for the frequency you want. So in any event, what you're going to do is you're going to call up and say, I am ordering a COM antenna, aviation band COM antenna, or aviation band nav antenna, or GPS, aviation GPS antenna, and proceed accordingly. Now the GPS antenna, or even cell phone antennas, the reason you don't see much of a ground plane is there's such a high frequency, the ground plane is like that long. So it's part of the antenna assembly. In fact, that's why they make a little hockey puck. The antenna sits in the middle, the ground plane sits out here, the antenna actually sort of runs in a little racetrack, and then in the middle, there's a computer that's doing a whole bunch of processing and amplifying and sending the data down the cable, or up the cable, depending on which way. Okay. So, dipole antenna will be balanced, but if we convert it to a monopole where you've got a ground plane and the monopole, then you're going to have to come up with some way of balancing it. Now, this can be done with capacitors and inductor in the base, or if you've got an assembly like a single pole, just a single wire with a couple of nuts on it type antenna, then you can install ground plane to one and monopole to the other, or if I have a dipole, I can just attach each of the dipole to each of these. Now what will happen is the electromagnetic radiation will hit both of these, and there'll be a voltage surge through the shield and a voltage surge through the shield, back and forth through the shield, back and forth through the shield, which will then incite inductively a surge back and forth the interior wire. Okay? Now the interior wire will get, and of course the length of this is going to be very, very critical, so that the signal length, the wavelength of the signal, isn't canceling the wavelength of the induced signal inside the center conductor. Okay? So that's one type of a balun. There's actually several different wiring configurations for a balun, but notice what they're saying right here. Okay, 1/4 of the frequency is going to be the length from there out to here. Okay, and then keep these guys relatively short. All right, so you may have to do something like that. There's another couple of different ways of coupling it. This is actually the same as that. This is a slightly different way of doing it. But the balun, or balanced to unbalanced converter, is sort of the handheld, or handmade way of doing it. That device, in the form of a couple of inductors or a small transformer, will be stuck inside the base if you buy the base type. It's all potted together though, so you won't be able to really see it. So here's an example of a couple of antenna arrays. So this one sort of shows some side reflectors this way, and then the driven element array that way. And that's going to try and make a big lobe coming out this way. Here, it looks like I probably got an array pointed this way, and then the two side lobe producers there, or your reflectors produced there. That's going to take a whole bunch of energy going this way, a little bit of backwash energy this way, and then because of this sort of cloud of energy, you're going to get some smaller lobes forming vertically, and maybe even a little bit coming out that way. But what we're going to do is we're going to say the gain is, what at this point, what would I get if it was straight omnidirectional versus what I get now that it's a shaped array. So the gain might be 10 or 10 times stronger. So if I'm trying to navigate or send a signal in a specific direction, then this is very useful. In fact, most of the time we do this.
So is that like a VOR antenna would be utilizing this?
Yeah, well, yes and no. One part of it is omnidirectional, the other part of it is absolutely totally directional. So when we get the VOR here in a little bit, you'll see what I mean. But ILS, glide slope, okay, very, very directional. Very specific, very pointed directional. Okay, a radar. Okay, you guys remember the big radar thing, right? Going around. Well, it's actually got the directed array or driven element kind of coming out in the middle. It's usually a fairly small thing. A nice big reflector that helps drive, but then also receives the echo back. Okay. Very, very directional antenna. Okay, so we've got to talk about the various different arrays and how they work. So the ILS and the glide slope, ILS, Instrument Landing System. Now, if you stop and think about that, Instrument Landing System, well, that would be everything you use to land, right? Well, it's not. The Instrument Landing System is actually only providing horizontal data, left to right. The glide slope system is providing vertical data. So we call the ILS one set of arrays, the glide slope a different set of arrays. One is going to be horizontally polarized, the other is going to be vertically polarized. Okay, locally horizontally polarized, glide slope vertically polarized. And these guys, the little note there that's kind of hard to see. Remember we said navigation is going to be 108 all the way up to 117.95? Well, what we're really gonna do is we're gonna say that a number of frequencies in that whole range are used for navigation, general navigation, and then specific frequencies, alternating frequencies from 108 to 112 are gonna be used strictly for close to the airport navigation. Okay? And the reason we need to do that is because when I tune to this, I'm also going to tune to a preset frequency for the glide slope. So for every frequency here, it's in a completely different band, but I have a unique frequency dedicated to glide slope. Okay, so those are all pre-arranged. That way you're not having to dial several different radios. So all you're gonna do is dial one radio. If it happens to be a general navigation frequency, then that's the way it's gonna work. If it happens to be one of these frequencies, the radio is gonna, not only is the data it provides to the meter gonna be different, but it's gonna pair to one of the glide slope frequencies, the one that's paired to the one it happens to be to. Okay? I think I say that. All right. So here's a monopole, and it's pumping out horizontally, and it's shaped to try and produce a very good horizontal wave being maximized, and not a lot of energy being transmitted upwards or downwards. Downwards, it's just going to bounce to the ground. Upwards, it's just going to go into space and annoy all those people that don't like listening to us, or aliens, or whatever they are. But as you can see, they model these things in really bizarre ways. And then, of course, I can put a building there and start creating echoes and all kinds of strange stuff. So the marker fan beacon, these are kind of all over the place. You'll note the array here. The elements kind of go out this way. What it's really trying to do is transmit straight up. Just a sort of omnidirectional, but straight up, and pointed up in an upward direction. If the airplane happens to fly right over it, what it's going to hear, it's going to be very, very loud. It'll be some tone, and it'll be very, very loud. Okay? If it's kind of weak, they know they're sort of close. If they don't hear it at all, they know they aren't over that thing. Okay, so I'm going to be using localizer information to sort of be this way. I'm going to be using glide slope information to be sort of this way, which will get me in the ballpark. And then when I go passing by this thing, I'll know I'm exactly X number of miles out from the end of the runway. Okay, so that gives me a pretty good three-dimensional fix. So we're going to call the first one the outer marker, the middle one the middle marker, logically, and the inner one the inner marker. We will intersperse things like, we'll call the outer marker the final approach fix, which doesn't make sense because it sort of seems like the initial approach, but it isn't, the final approach fix. So the vernacular here from the pilot side is a little confusing. Then what we're going to do is we will transmit on a very specific frequency. I think it's 75 megahertz. Does it say there? I don't remember what the frequency. But what we're going to do is we're going to transmit 3 different tones. Okay, it looks like 400 hertz, 1300 hertz, and 3000 hertz. We're going to transmit those tones, and that's going to go into your audio if you have the outer marker beacon turned on. You'll hear it beep, 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 or beep, 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 or even higher, right? For the 3. Many airports, by the way, don't necessarily have that inner marker. Because it's just it's not necessary, because the airport doesn't allow those kind of minimums to where it's helpful. But the other thing we're going to do is the device that's listening to this is it's going to listen for that tone, 400 hertz. And if it hears the 400 hertz above a certain threshold, it'll start causing a light to go beep, beep, beep. In this case, it'll be a blue light to start flashing, and you'll hear it on the audio if you've got the audio set up. Okay, then it'll start getting weak again. And then a little while later, the middle one will start coming beep, 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 get really, really loud. So that gives the pilot some distance information and a double confirmation that they're probably in the ballpark for headed towards the end of the runway. They call that a fan, and it's a beacon because it's just a beeping, but doesn't really give you any other information.
Are they phasing those out?
Oh, absolutely not.
Really?
No, that's part of the ILS. There are places where you don't need it anymore because a lot of folks have GPSs, and the predominant users that they're using DME, other types of equipment. But there are still many airports that use them. I can tell you Gillespie still works, Palomar still works. Palomar you can actually get to fairly easily. You guys know San Marcos, where San Marcos is? You get off on 78 on San Marcos Boulevard, there's a Home Depot right there. Kind of just a little bit to the north side of, right? There's a big hill that's kind of towards Palomar College. There's a big hill, just sort of like, I don't know, 200-foot tall hill. Well, Palomar's outer marker is right on top of that hill. You kind of get an angle. You can see it's this funny little antenna. It looks just about like that one, sitting on top of the hill. And that's exactly 5 miles from the end of Palomar Airport's runway. Okay. So here I talk a little bit about some radio theory, how the basic transmitter operates. So at some point we need to create the carrier frequency. Nowadays we do it via digital. It used to be we would actually take a piece of crystal, a piece of rock, crystalline rock, tuned to a specific frequency, run electricity through it, which would create this oscillating signal. Okay, we would then vary that to whatever, tune it to whatever frequency we needed, and then once we got that nicely tuned, we would then take and add the data to it. So the oscillator is going to create that original AC frequency. We're then going to amplify it. We amplify all the time. Things get weak, so we amplify. The modulator is going to take whatever's coming from the microphone, whatever's coming from whatever data we need, and we're going to run that into here. And the modulator is going to turn that into an electromagnetic pulse on the wire. So again, the microphone. And what the microphone is going to make the data, and then the carrier wave is going to come down. And the modulator is going to bring the two together to create your amplitude or frequency modulation or digital modulation. Okay. And again, the frequency generator at this point is going to be this is what's going to allow you to pick different channels. Okay, so the basic carrier is going to be for the band, and then this is going to allow you to modify it to a different channel, 101, 107, 98. Amplify it again. We love to amplify. And then shove it out the antenna. If I don't have an antenna that's creating this big magnetic pulse, what I'm now going to have is a fair amount of voltage and current here going nowhere. So it might try to go somewhere inside this output amp, which would be bad for it. Might even break things further back up the line. So never, ever, ever receive, no problem. Transmit, never, ever, ever transmit without an antenna attached. Particularly without the appropriate antenna attached. Then the reverse is going to be antenna, electromagnetic radiation going causing electricity to go back and forth in the line in that various whatever waveform. And the truth is, there's all kinds of different frequencies being picked up by this, right? However, higher and lower frequencies aren't going to move the electrons too much. Just those frequencies that are the right length for the length of the antenna, they're going to create the most action. So the value of having a sort of narrow band of sensitivity for the antenna is its physical length sort of filters out all the rest of this unwanted noise. The problem is that physical length, you can have multiples of that physical length that will, oddly tune in for brief periods of time, other frequencies. That's why every once in a while you'd be just flying along and all of a sudden you get another frequency and just bleeding over. Okay, again, it's pretty weak signal. We'll amplify it. We'll then use the tuner to narrow into which channel we want to listen to within that band, which means all the other frequency or all the other data oscillations are going to be tuned out, shunted to ground. The demodulator will then separate the carrier frequency from the data. So the amplitude modulation data or the frequency modulation data. Okay, and then the carrier, we don't care anymore once we pull it out. What do you think we're going to do next? Probably amplify it. Okay, yeah, we're going to amplify it again. So in this case, we're going to presume it's intelligent. Depends on who's talking. Might use a speaker, might use an instrument, might use a computer to do whatever, and then present the data, etc. Now, again, these are sort of the basic blocks. Something not shown here in the actual radio. You'd have a power supply, you'd have filtration, you're going to have a bunch of human interface controls, a number of other things. But this is sort of just a logic model for a radio. It's also entirely possible that you could use different components like the amplifier, depending on whether you're going to transmit or receive. I can use the same amplifier for both. I just have a couple of relays pop out and put the other part of the circuit in. This one shows a very big bird. Let's see, this is a 767 extended range. And it's got all kinds of little whistles and bells sticking out around there. GPS, several GPSs, TCAS, VHF, long range, or your left and right one. Second TCAS. That's probably a port. Some of the navigational stuff's going to be in the nose. Okay, weather radar, that's kind of nice up there. Again, also more navigational data up here. High frequency transmission for long range stuff if you need it. You might have SATCOM, some of the Southwest where they got the little cell phone biscuits put on top. That's actually satellite antenna array. So again, other navigational stuff, the marker beacon antenna, distance measuring equipment. Looks like there's a left and a right there. Might also have a radar altimeter. What it's really doing there is it's sending a pulse downwards, just like a radar does. It's a very, very limited pulse heading downwards, hits the ground, reflects back, tells it how far away it is. This one's kind of interesting. What they do is they take advantage of the Doppler effect. When you drop the rock in the water, the wave goes out, and the further it goes out, the wider apart it gets. So if it's traveling at the speed of light, you go ping, goes all the way down to there, comes all the way back out. You know how far it was when you sent it. Now that it's a little bit longer, you measure that, and that tells you how far it went both ways, and it's remarkably accurate. Things can mess it up, like I hit water or I went over some bushes, but if it's averaging it out, it gets a pretty accurate, to within 20 or 30 feet. And even more accurate if you're going over fairly smooth terrain. Oh yeah, so here's a couple of different kinds of antennas. Here's one. Oftentimes you see something like that, you think nav antenna, but no, this is a comm antenna, meant to be very aerodynamic. Note how it isn't very long. what did we figure out? Didn't it need to be about 3 feet long or something like that? When we figured out the middle of the band and did all that math, 33 or 300 million divided by the frequency that we're dealing with. Well, again, what I can do is I can play with a capacitor and an inductor and change the impedance of that antenna to cause it to be tuned to the right frequency. Or, for example, like this one, the antenna has to be that long. There's nothing that says it has to be perfectly straight. So I can make it that long by taking and doing a spiral wrap inside this little composite tube. Okay, and then just curlicue it some. So a lot of the smaller radios with the little flex biscuit on the end of it, that's what they've done. They've just taken the wire and made a curlicue out of it. Does that interfere or reduce the strength a little bit? Yeah, but those things weren't made to be long range anyways. This will work. Here's another one where it's a straight conductor, and that's probably still a little too short as well. So they've used probably an inductor in there to cause the antenna to seem like it's a little bit longer than it really is. This here is the one I was trying to draw here, where you've got some insulator, maybe a couple of gaskets, and maybe even a stiffener in there. The two insulators come together. The antenna rod comes out here with a couple of clamping nuts to hold it in place. And then at this point, you're going to have one lug of the monopole coming in here, the other lug of the coaxial, and they don't show this, there needs to be a balun. The other lug of the balun would then connect to your ground plane. Okay, and they don't really show that as a balun, but it needs to be one. So now here we're going to start getting into a little bit more sophisticated. We're going to take and horizontally orient the antenna because we're looking for data that's giving us a direction. Okay, so we want oscillation data that's going that way. It's going to give us a direction. And what we really want is we want it to be nice and straight out like this. But that's not very wind friendly, is it? So it turns out it works pretty well if we curve things back to roughly 45, which greatly reduces the wind loading on as well as the amount of drag. So here we do some aerodynamic shape and make it look really pretty. Here we just stick it out and a couple of wires sticking out, a couple of whiskers sticking out. These guys, because of where they often end up, you want to put them somewhere where as you walk up to the airplane, you're not going to kick and bend the darn thing. So on top of a vertical stab where you got to get around the horizontal stab to get to it, right? Or there on top of the cabin. You know, and even then, if I'm standing on the wing with the door open and I bend over, I might bang that sucker, right? If you bang it, it's going to hurt and it's going to damage it. And I can assure you, that antenna right there is probably about a $600, $700, $800 proposition. So you kind of don't want to break it. Okay. Distance measuring we're going to do at a much higher frequency. And again, this is going to take advantage of Doppler effect. This type of antenna also is commonly used, although it's a different frequency range, for transponders as well. Transponders are 975 megahertz, something like that. Okay, and I don't remember what frequency the DME is operating. So here's your glide slope antenna, and again, the glide slope needs to be oriented on the vertical, so it's going to sit here. In all likelihood, this is going to either sit down or the bar going to face down, or it may actually be in an area, like let's say I've got the top of the vertical stab has a nice big composite, tip on it. I might be able to take something like that and put it up in the composite tip so that it's hidden, but the composite material isn't really going to interfere with the transmission being sent to it. Now, it's also important to note that the glide slope, the only time it's used is when you're pointed right at the runway, right down the runway, and when you're passing the runway if you do a missed approach. That's the only point that that antenna is going to be used. So you're going to be having an antenna array, so it's a pretty heavy duty radiation at you. Not enough to toast your gonads, but that signal, that antenna really isn't that great of an antenna. That's okay. So now an ADF or automatic direction finding antennas, they're all going to have, this is very old, they're going to have some element in there that rotates around. Even these ones have some elements that rotate around in there. And what we're really doing is we're saying, I'm going to tune into a frequency. Well, in truth, what we're going to tune into is AM broadcast stations. Because that's what we had originally. So this is very early technology. All that we had out there was AM KCBQ. I don't know if that's AM, but whatever, you know, whatever the local AM broadcasting stations are. On your chart, your sectional chart, it'll tell you where KCBQ's antenna is. I think it's KCBQ, that's the one that's right there by 52, the three big antennas sticking up. So your chart will say that frequency is right there. So now what's going to happen is this guy's spinning around, it's going to go, you know, rock and roll, rock and roll. Rock and roll, rock and roll, rock and roll. Okay, rock and roll, it's going to get loud. Now, whatever point that is, as you're looking at the needle display, you're going to realize that usually it's pretty good at saying which was stronger and which was weaker. So you can tell what direction it is from you to, on a radial heading, to that radio station. So now you get on the chart, reverse your values, draw a line out to here. Then listen to another radio station, draw a line out to there, I must be right there. Of course, by the time you do all of that, you crash the airplane. No, by the time you do all that, you probably moved a little bit. But that was what they had at the time. This is definitely phased out, but in truth, the system still exists because we have all the AM broadcast stations, right? They all still exist.
Did they triangulate with that too, or was it just tuning, like trying to get on a beam, the strongest beam?
Well, you would only use it really for triangulating, unless the radio station happened to be pointed, you know, right in the right spot for the runway. But so you would always triangulate off of two radio stations, get a radial to you, and it's very rough line to you. Okay, and then cross, and that's about where you are.
So it's a precursor to the VOR then?
Yes. So GPS, much higher frequency. So it actually wasn't Garmin, I'm trying to remember the name of the company, but there's another company that invented the idea of taking this whole thing and putting it into a little hockey puck. And it's actually can be up to 12 different antennas in there, all listen to the satellite data, getting and collecting satellite data, processing it in there, and then transmitting data down an antenna line. Most of the time, these hockey pucks, they're not passive, they're active. What that means is the inner conductor and the outer conductor actually have a small amount of voltage on them. And that's what powers this thing. And then it modifies and sends a signal on that voltage line. And you say, well, how does it do that? Well, there would be our AC signal, but if I've got DC up here like that, then I can just shift it up some. Okay? So these become very, very active. So Garmin bought the idea and then made a zillion of these hockey pucks. Then a whole bunch of other people said, well, let's buy the Garmin hockey puck. I think it was a GS 150, was the original model number. So all the other manufacturers of aviation and GPS antennas kind of bought and rebranded Garmin's antenna. Now most of them make their own stuff. Okay, so short range communication, typically meant to be line of sight. So if I'm transmitting fairly low, something like about 10 watts, which I think is what the ATIS and Gillespie transmits, I'm flying along. If I get behind Palomar Mountain to the north, which is 45, 50 miles away, I can't hear the ATIS at all. But as soon as I clear the mountain, I start hearing it pretty readily. I can hear the tower just fine because they're transmitting at 25 watts. Okay. Rarely would you find a situation where you've got a transmitter, that's like LAX or Ontario, that truly can transmit 200 nautical miles across the ground. However, up at 40,000 feet, now it's real easy to get straight line 200 nautical miles. Okay. Down low, because of the curvature of the earth, you're going to be behind the earth. So that's why there's both a line of sight requirement and still no more than about 200 nautical miles. So this is true for all communication and for aviation, which means no matter what, you're going to have an antenna at least every 200 miles. Well, we've got a lot more antennas than that, but we can mount it on top or the bottom. Obviously, on the bottom, you're going to need landing gear long enough to not wipe the antenna off. On the top, it's maybe a little bit more prone to leaking and getting bumped. Both work. Needs to be vertically polarized, and you're better off being out on a wing so that you don't have the landing gear exhaust or propeller in the way as you're heading to or heading away from. So it's a little better to be out on the wing. Not very convenient to put it out on the wing though. So more often than not, you'll see comm antennas being mounted on the fuselage. And if you don't have a propeller up front because you've got the mount on the wings, then everybody's happy. So I would say universally monopole, except I happen to know somebody who's got a dipole on their little bitty airplane. Okay, so there's all kinds of different things happening there, but the little airplanes talking to each other. So some of the different communications radios, there's some really fancy ones. There's a real nice Garmin tuned in. That is Oshkosh Towers frequency, and that is their ATIS. I concur. Tuned into that many times. Dynon, they've kind of done a cool little deal where what they've said is the radio magically sits anywhere you want it. It's got some wires that then feed into here and a little panel that feeds into here. And so your radio data is right here as well as here. And what I can do is I can say, okay, I'm going to plug all this stuff in. I'm here and I want to fly from here to here. And when I'm at this airport, this is what I want to do. And I hit the button and go poof. And it pumps all that data over to here. And now if I want the tower, I just push tower. And it puts it into there. Or if I want ATIS or ground, I put it in there. Then I hit the flip-flop and trip it up to the active. Okay? Very, very common in aviation. In fact, I don't know of one that doesn't do this anymore, to where you have what's called a standby frequency and an active frequency. So any changing you do to the standby, and then flip it into the active state. Now, if you only have a single radio, this is kind of handy. You know, pulling out of between the hangars, flipped on the ATIS, listening to ATIS. Meanwhile, I've tuned in the ground frequency. Okay, get ready to talk to ground, pop the button, ground's now active, tune in tower frequency. Okay, talk to ground, tell them I don't like them, but where I want to go, and then change my attitude and say I'm going to buy them chocolate. They give me permission to go. I go up and do my run up, pop the frequency again. Now tower is active. Tune in my in-flight or maybe TRACON or whoever else, or if I'm flying formation, whatever discrete frequency is, whatever, I can keep popping along. Well, this automatically populates it for you. Okay? Then once I get to sort of where I'm going, I come over here, plug in destination, hit info, populates the new airport. Okay. Garmin, what they've done is somewhat like this. Is this the 530, I think? No, it's the 430. This one, what we've done is we've sort of said navigation here, map and all this kind of stuff, common VOR stuff here. So all my comm frequencies and flip-flop are going to be here and stored here, and VOR ILS navigation stuff displayed here. However, this will provide all the nav data. I'm going to need a separate display for the instrument that shows my ILS VOR glide slope data. This display is going to give me all kinds of map view, right, as well as GPS data. Here's another little radio. This is made by some guys in Europe. The nice thing about this is it fits in a 2 1/4 inch instrument. Okay, standard 2 1/4 inch instrument hole. Screw it in, sticks out the back. Kind of handy. Yeah, all of these have lots and lots of wires.
What's the output of a handheld radio typically? A handheld?
Typically no more than about 5 watts. And they say max output is 5 watts. What they're really saying is if you're at that one frequency that the antenna is really well tuned for, and nothing else is going on, and your battery is really well charged, and you might hit 5 watts. But pretty much anywhere else, you're not going to hit 5 watts. Because those little rubber biscuit antennas aren't that great. All right, let's, what did we do? Yeah, I ran over, so let's see, that would be 20 till, how about 15 till?